So here is where we left off. So you remember that there is this thing of evaluating a function at C and of plugging C into the function, right? So that's the evaluation, or taking the limit. In other words, you plug something very similar to C, but not C itself. Okay, so you remember what this table is supposed to signify. The table, by the way, is not what you truly do. The better analogy is that water gun cannon. Do you understand the water gun cannon analogy, guys? So a function, what does it do? It takes points on the x-axis and it maps them onto the y-axis. When you draw a graph, that's only a representation of how each particular x correlates with a particular y. But what you might imagine happening is actually that the points go and they're thrown onto the y-axis. Good. So when you take a limit, what you can imagine doing is that you have an open faucet. It's like water on the x-axis. You have an open faucet or an open pipe, and you squirt all the water inside of this pipe. This is the blue pipe, except for the one target point, which in this case is supposed to be -1. And then what you do is you close this pipe, you narrow the opening smaller and smaller around, let's say, -1. And if the limit exists, you should see that the stream that comes out of it, the current, will get focused around one point, in this case, around the point 2. And that will be the delta epsilon definition of limit. And maybe I'll just wait, I'll explain today's lecture. And then by the end of it, I hope I will not forget, I will ask you if you actually want to consider this delta epsilon, right? I have a video about it in a class I presented before, actually in-person class, but we can have a discussion of it if you would like. So, because you see, everything that we do here, hopefully it's not arbitrary. Hopefully it will be something that you understand and understand very simply. So there are also one-sided limits, and one-sided limits means approximation. Let's say in this case we approximate C, but we can approximate C from the right or from the left. So this means I grow towards my C, so that's X going to C from below. That's what the minus means on top. And this means I decrease to C, which means I go to C from above. And we did this example, so you can see how these limits are formed. Naturally, the total limit, if I don't specify a sign plus or minus, that means both from below and above, and it can only exist if the left and the right-hand side limits are the same. So a very basic example would be, let's say, limits from graphs. That's where it begins, right? And so what you imagine is you have a landscape, and this landscape is generated by a function. So this is y equals f of x, okay? The fact that there is this hole, that means this function is undefined at 5, okay? So what is this graph? This is the graph of combination coordinates x, comma, f of x. That's the altitude, okay? So f of x for this landscape specifies how high it is above the x-axis. Make sense? Type yes if it makes sense, guys. That's also a way for me to see that you are here. Wonderful. Thank you. And so, yes. And so what happens here? So for this problem, let's say without me further explaining, one thing I mentioned the last time is many people said it's a two-dimensional landscape, but that's incorrect. It's a one-dimensional landscape folded inside of a two-dimensional space, right? So what you're confusing is the x and y axis. Dimension is the minimum number of coordinates or numbers that you have to specify to describe a location. Our space is three-dimensional because in general, you have to specify 3 coordinates to locate a space. And that's a very complicated kind of interesting idea. It goes into the notion of what sort of space we have. There are some theories I can show you with space filling functions where the space might in fact even be one-dimensional. The question is, what's the minimum number of coordinates required to specify a given location? So what you have to do for this example is figure out, yes, for example, Joshua, wonderful. Your pitch and roll is one example of three-dimensional space. So anything you try to describe in the space, you require the minimum of 3 coordinates. There are some other very interesting conditions that you actually get into. But roughly speaking, this space is one-dimensional because you can imagine it's like a ruler that you folded or bent, and you can imagine the marking. So if you are attached to this particular curve, you only need 1 coordinate, okay? But the curving is, of course, described within a 2-dimensional framework. So what I want you to know is tell me what is f of 5 according to this graph, and what are the left and right hand limits, and whether or not the common limit exists. Good. So type in your answers. You know, you can write A, B, C, and the answers. All right, guys, go ahead. So far, I see only 2 people. Well, I see replies, but less than 30. And thank you, Kirill, for opening up your video. All right, if it's a nuisance to answer, you know, B separately, you can answer C right away as well, right? Okay, thank you, guys. So indeed, the answer is that in A, there is no answer there, right? In other words, doesn't exist because the doll cannot stand over this hole. B and C, I mean, you can just answer C. C already implies B, and yeah, C implies the left hand and right hand limit. So clearly, by the graph, it looks like if we move the x coordinate of the doll towards 5, either from left or from the right, the doll will hover close to the elevation 2. So here it seems like it stays at 2, but if you move it from the left, if you move to 5 plus, then the doll is descending to 2. So it will be like 2 with a plus on top all the time, right? So it's slightly over than 2 or bigger than 2, but you are getting towards 2. Good. So here is a slightly more complicated picture. I'm not sure if you can read it because what I try to draw is impossible to fully draw, but examples like this exist, okay? So for this example, can you see it, guys? What do you think is f of minus 1? Does it exist, f of minus 1? You see, what you look for is solid curve or a solid dot, okay? What's f of minus 1? What's the left and right hand limit? You know, obviously towards minus 1, that's the point of interest, and whether or not the full limit exists. So this, because I'll tell you afterwards what this picture is supposed to indicate. But for now, let's see what's your intuition. And again, guys, I would like to repeat my request. Open up your faces. I want to see you. I want to hear from you. I'm pretty sure that in most other classes, it's required a bit harsher than what I do. I just do not like to pry into your private life, or maybe there is something you're ashamed of. I hope not from me. There is absolutely nothing you can be ashamed of from me. You know, I am, yeah. So, or another thing I would like to know, if you're not opening the camera, could you then explain to me why you're not doing that? So Joshua, you're saying touching the curve, you think it's -2. Well, so first of all, what's f of -1? I'm asking, right? What's f of -1? So Ping, you say -2. Thank you. Right. So you see the position at -1 here. It's at this nail at -2. So the doll is here. So the answer is -2. The function at -1 equals to -2. Now the question is, what about the right hand limit, right? What about if I walk the doll along this curve? So x is moving towards -1. What will that be? So Kirill, yes. So limit on the right side is 1.5. And the limit on the left side, guys, what do you think that would be? Yes.
It doesn't exist? Oh.
It doesn't exist. Oh, thank you, Alexa. It does not exist. Let me try to explain to you. So I cannot draw it because to draw it, I would have to move my arm up and down infinitely many times. And I'm already tired after finding it many times. Fingers crossed, right? Trust me, right? I write those notes. It's pretty much, well, it's pretty interesting how things are. You know, many things that I do, I know absolutely they are useless, right? Sometimes I think I talk to you and that's meaningless, right? Like a lot of things are meaningless, but you do it. That's maybe why Sisyphus was carrying the stone up the mountain. He probably knew it's useless, but there are certain compulsions that cannot be stopped, right? And I was in the past, 5 months and whatnot, I realized that even more, right? That's just, it's like being driven by water, by a current. So the idea here, guys, in such curves, I can prove mathematically. I can give you examples later on, right? I don't want to introduce complicated examples just yet, but there are examples of curves that will be folded up infinitely many times. You can actually see such a curve in some sense. You can see, if you know the sine curve, right? The sine wave, if you believe it goes infinitely far, you just take a spherical orb and reflect it. The infinity will be reflected to 0, and you will have this pattern. So if you walk the doll on the left, it will go up and down, up and down, up and down. It looks like it oscillates from 2 to 0.5, up and down. So move closer, it's higher. Move a little closer, it's lower. Closer, higher. Closer, lower. So the doll keeps jumping up and down faster and faster, right? So you have the valleys and the peaks appear more and more frequently. So that's an example where, well, the right-hand limit is not that interesting, but the left-hand limit is divergent by oscillation. You see, so the left-hand limit can exist in this rather strange way, where there's just oscillation. If you actually try to simulate it with the squirting of the water cannon, you will see that that the current, you know, if you've played in the summer water guns, right? So it shoots a fairly straight, fairly narrow stream. So in this case, the stream is never narrow. The droplets fly all over. No matter how little water you squirt, the droplets fly all over. They are spread very widely. So the limit does not exist. You cannot focus this current. You understand? It's like a rusty shower, if you ever seen one, right? So no matter what the water is, the water is just sprayed in all directions. All right. So now let's talk slightly about infinite limits. Yeah, so the water lens, no matter how small, no matter how narrow is the left side of the pipe from -1. So here's what you imagine. I hope you can see my camera. So you have -1 and you have the left side of the pipe. The left side of the pipe, the water there is, you narrow it, but the spray still covers any point between 0.5 and 2. So just, you know, it's not disappearing. Okay, good. So next time I want to know, well, limit at, well, infinite limits, right? So could you try, let's see if you can do it without my help first, and then we'll look at it. We want to try to predict what's the limit as x goes to 0 of 1 over x squared, and whether or not it exists, okay? What do you think to do here, okay? So you see, I clearly cannot plug in 0. That's one first reason that we introduced limits, is that we're trying to make it rigorous. What do we mean by counterfeit, right? So I cannot plug a 0 here, but when I take limits, I can plug counterfeit zeros. You understand? Because I can divide by fake 0, something that is very close to 0, but I cannot actually divide by a 0. And I hope I convinced you. Right? If I haven't convinced you, you are welcome to argue about it. It's, by the way, if you go to complex analysis, things are confusing. You can divide by 0 in complex analysis, you understand? And I can explain what that means. But for our number line, it's not something we can define. Oh, Zainab, hello. Thank you for opening up the camera. Nice to see you. Kirill, yes, thank you. Exactly. And we will look at it in a moment. So, guys, I want you to see what happens here. So, here is what we're doing in terms of a table, right? So we're plugging counterfeit zeros. I want to plug right away either plus or minus. It doesn't matter when you square. By the way, here's another interesting question. Why positive times positive is positive? Let's say that's clear. But why negative times negative is positive? I wonder if you can come up with an argument. We can talk about it later, right? But think about it, right? You learned so much in school, or memorized, better said. Have you thought about it? Why negative times negative is positive? So regardless, for a moment, let's ignore this fact, since we need to talk about other things. What we have here is if I square a positive or a negative number, I get the same thing. So this is counterfeit 0. It's 1 over 10, right? I square it, and I put it on the denominator. Dividing 1 by 1 over 10 squared is 100. Everybody sees that? Why? What is that really, guys? You see, so everybody sees that 1 over 10 squared is 1 over 100. So this means 1 per 100th part. So when you divide, you really specify the answer, how much does one person get, right? So when you have 12 apples divided by 6 individuals, when you say the answer is 2, you're saying one person gets 2 apples, okay? So what you do here, you divide 1 apple by 100th of an individual. You're saying 1 apple goes to 100th of the individual. So how much the individual gets? Well, an individual is 100 parts of 100, right? So the individual gets 100 apples. You follow? Cool. Right, so it's pretty simple, right? So what do we have here? Here, if I plug a better counterfeit of 0, I get 100, well, I get 10,000, sorry, right? And I plug 1,000, I get a million, right? Just square it. And so as you see, those numbers are better and better approximates of 0. So they are better and better counterfeits of 0. As I go there, what happens to those numbers? They explode. And you mark this by the symbol sideways 8. Good? So, by the way, this is a question. So we get this symbol 8, this sideways 8, this infinity. So does the limit exist or does not exist? And guys, again, I want to see your faces.
So does that mean the limit does exist, but it just happens to be infinite?
Well, you can try and say that. So you're saying it exists and it happens to be infinite. So Ibad says because it's not an actual number. Okay, so the reasoning is this, guys. So in calculus, this symbol has different meanings, right? It depends on the context. Okay, so we see so many things that are confusing in your life. It's because of the wrong naming. You see, so you might get associations because of a name, associations that are not correct. Okay, so the situation truly is much more complicated than exists or not. But in real numbers, right, in calculus, the meaning of this symbol is it's just growth without bound. So you say infinity, but it is not the right name for it, right? There is an actual infinity in mathematics, and we can possibly talk about it, and they are vastly different between this symbol. Okay, what this means, you should imagine like a balloon. That's what I imagine. Let's say if it explodes, so the balloon is being puffed with water, and the balloon is expanding. At no moment of time is the balloon or does the balloon have infinite volume. It just expands and expands and expands. It gets larger and larger and larger without there being a bound. So this means more so growth without bound. Okay, so it's not a number. This is just an indication that we have an explosion in the size of quantities, right? So they grow and grow and grow and never stop growing. So they will be bigger than a billion, bigger than billions eventually, right? And that's very important to know that, because later we will see different rates of growth. You understand? When we consider this symbol divided by itself, some people might want to say it's 1, but this is just expressing numerator and denominator are competing in their growth, okay? And how fast each of them grows might determine the outcome, okay? So this is not a number in our context, so you would say the limit diverges or does not exist, and you would say the numbers grow without bound. But it gets tiresome to say grow without bound, so you say grow to infinity, okay? But you remember that it's not infinity that we have here, it's really the idea that something expands without stopping, okay? Or becomes taller without stopping. So that means that if I walk my little person on this curve, as I walk the person from the right or left, I will see that the person is climbing steeper and steeper and steeper and steeper and goes up, and he's climbing a mountain that does not have a top. You understand? Wonderful. So here, guys, is the next problem. Let's see if you can figure this one out. So we have 2x over x minus 3, and your goal is to predict what's happening here, okay? What is this thing doing? And you tell me the limit as x goes to 3 plus, and tell me the limit as x goes to 3 with a minus. In other words, to the right of 3, moving from the right of 3 towards 3, or from the left of 3 towards 3. What's
Do you have to graph it?
Sorry?
Do we have to graph it?
No, you can if you want to, but what I really want is for you to predict what is the limit going to equal to. You don't need to graph, right? Very often graphs are complicated to generate without a machine, sometimes even with a machine. So what you try to do, you try to orient blindly. You try to feel your way with the senses of mathematics. Understand? So you don't actually see. You're like, the analogy is like you are a worm, or you are a golfer, or whatever it is, right? So you have no eyes, but you still can figure out your way through it. Steven, thank you for showing. Well, but how infinite? Okay, so Kirill, try to describe what's happening. Left and right limits are possibly different.
Professor, so I plugged in. Are we supposed to plug in or no?
Well, you see, don't ask if you're supposed to plug in or not. Think about what's happening here. Am I plugging in? What am I plugging in? What's happening? Okay, you see this? So plugging in is just it's not complete sentence. Do you plug in? Do you plug in 3?
Yeah, that's what I'm.
You plug in 3.
Yeah.
Right? Do you plug in 3?
Yeah, because it's an x,
but
right?
it's a limit. It's a limit.
Oh wait, no. Okay.
You see what I'm saying, right? So you just have to remember what the sentence means, right? Grammatically, you are plugging in, but what? So you say, do you plug in? But what do you plug in? You don't plug in 3, right? Because it's a limit, right? So the process means what? What do you plug in?
So anything but 3?
Well, more precisely, anything but 3 that is nonetheless very. Complete my sentence, or?
I don't know.
Very, very limit. What do you do? Very
get as close as you can to 3.
Close as you can to 3, right? So you imagine plugging in, but values that are counterfeit 3, and in particular counterfeit 3, but above 3. Okay.
Okay.
And I'll show you how I do it fast without the table, right? And yes, close to 3, exactly. So 2.99, you can plug in 3.01 or a bigger number if you have a calculator, but you should try to avoid calculations. You can predict what's happening without calculation. You understand? And you got my email, correct, guys? It was sent last night. I'm not sure if you had a chance to read it, but I hope some parts are interesting. I'm interested in your answers to this email. Yes, Fatima, you can plug in numbers like that, but you can do it even, you can imagine plugging something in without actually being very specific about it. You should imagine more so that you plug in numbers like 3.001, but not necessarily actually carry out the calculation, because that can be tedious. Okay. So are we ready, guys?
Another question. So when it comes to approaching from when plugging in anything but 3, when it's approaching to the left from the left side, do you use a negative number? Wait, left. Yeah.
Well, to the left, but because 3 is not a negative number, so how do you approach 3 from the left? So you use 2.999, right? Because it's slightly smaller than 3, so you think more so to the left and to the right. If it's around 0, then of course it's a negative number, right? But to the left of 0. But if it's just anything else, then not necessarily. So Anis, let's see. So you are correct. So I hope, guys, you understand. You're not just doing calculus. Hopefully, slowly, you're building up your imagination, okay, in your ability to reason well. Very, very few people can reason well. I do not know if I can reason well. And if I can, only on brief moments of time. Most people run their lives entirely on automatic. Not even 1% of their existence is conscious. Right? I'm not sure mine reaches 1%, but I try. Yes, I will explain everything. Ping pong, ping. Sorry for mispronouncing your name. That's good. That's good. Confusion is the precedent of understanding. You know, people that are not knowing anything, they are never confused. They think everything is simple and they understand this universe. And once you start thinking, you realize you don't understand anything at all. Okay, guys. Well, what is this saying, the limit, Fatima? Think about it, right? What is this limit saying, right? So you're not trying to figure out what to do so that some old man leaves you alone, right? What you're trying to do is you read it as a sentence and you're trying to get to the meaning. So what we have here, let's do it together, guys, okay? So one thing you can do, by the way, is to recognize that this is not really a new function. You might really want to have here, you know, instead of x, you might have preferred to have here x minus 3 because then it would cross out. So that's one thing I sometimes do. It really helps you. Not necessarily this problem can be solved very quickly, but in general, that's a good practice. You understand? You call it, I call it at least wishful thinking. If you don't like a problem, you try to figure out what problem would you have preferred? How should it look like so that you would have preferred it? And if you can figure that out, you can modify it slightly, right? So you pay for it, of course, but you modify it and then the problem becomes much easier. So it's a problem of recognition. If you are good at recognition, all the many problems we'll solve in this class will look to you like maybe one problem, one or two problems, just, and then the subject is so compressed. So here I would have preferred to see I factor the 2. I would have preferred to see just to say I cover this this 3. X minus 3 over x minus 3 would have been 1, right? So what I do, I subtract 3 and I add 3, and then I distribute the x minus 3 to x minus 3 here and to the 3 here. So here they cancel out to 1, and here I have 3 over x minus 3. And then I multiply the 2, and I have 2 plus 6 over x minus 3 on the bottom. So I can reduce it to forms that I've seen before, okay? But for this problem, you don't even need to bother, you see? So here is what I do. I don't plug in 3.001, right? Because it's calculation. Why would I want calculations? What I do is I plug in 3 plus and think conceptually. 3 plus means all the numbers you can imagine slightly above 3. Now tell me, if I plug 3 plus on the numerator, type or talk, what do I get in the numerator roughly, guys? I plug 3 plus in the numerator. What roughly am I getting in the numerator? You can do it.
6.
6. Beautiful. Thank you, Alexa. That's 6. In particular, 6 plus. If you really, it's not important. 6 or 6 plus are not going to be a big difference, right? Really, 0 plus or 0 minus can be a big difference because 0 minus is negative, 0 plus is positive, right? But 6 and 6 plus, essentially, it's a 6-like number, right? So if you plug in a 3-like number multiplied by 2, you get a 6-like number. That's my language, okay? So you get a 6 on the top. Good. What do you get on the bottom if you plug a 3 plus? And be very careful about it.
A 0-like number?
A 0-like number, but here it's important. 0 plus or 0 minus?
0 plus.
0 plus.
Beautiful, because it's slightly over than or bigger than 3, so it'll be 0 plus. So you essentially have 6 divided by 0 plus, which means 6 divided by 1 over a million, right? And you can see that means what? That means essentially 6 times a million, correct? Because 6 divided by 1 over a million, you just take reciprocals at 6 times a million. So the answer is positive infinity. Clear? So this is right away positive infinity. Because it's 6 divided by 0 plus. If you divide if you divide a positive number by something slightly bigger than 0, it explodes to infinity. Clearly? Clear. Right? It's clear. It's clear. So, and what about here? The second part, if I plug in 3 minus, what do I get on the top?
6 minus?
Yes, and on the bottom?
0 minus?
And what do I get as a ratio?
6 minus over 0 minus?
Which would be?
Plus
Undivided.
infinity.
Sorry?
Oh.
Yes. So 6 minus or 6 plus? No, the 6 minus means slightly less than 6, but it's positive if it's slightly less than 6, right? But 0 minus is important. So you can write, you see, you don't have to distinguish between 6 plus and 6 minus because they are essentially 6, they're all positive, right? But 0 plus and 0 minus, they have a quality, right? 0 plus is positive, 0 minus is negative. So it's important really to keep track of 0 plus or 0 minus. So really, I did it, I kind of factored it, right? I didn't, this step is not necessary for this problem. I just wanted to illustrate an extra procedure that is often very useful, okay? So here I plug 0, essentially I have 6 over 0 plus, right? And here I have 6 over 0 minus. Now 6 over 0 minus is negative infinity because I divide 6 by, let's say, minus 1 over a million, which is the same as to multiply 6 by minus a million. So the answer is minus infinity. So this goes, falls without bound, it goes to minus infinity without bound, and this grows without bound, good? So the combined limit does not exist. What about the separate limits? Does this limit exist? The limit as x goes to 3 from the right, does it exist? No, because this is just, the numbers are just exploding without bound. It's not exist here in our context means you are getting a number. Infinity or minus infinity is not a number. It's just a qualification of how this limit diverges, right? So plus infinity means grow without stopping. Minus infinity means go down or plummet without stopping. Good. And that's the end of this lecture. Let's move to the newest lecture. So those are limit laws. So you see, constructing a table, not only is it not rigorous, and not only not rigorous and also tedious, it's not a good procedure for most questions. It's not efficient. Okay, so the limit laws is something that I can prove to you if you're interested. That's can be proved using delta epsilon. They're not arbitrary, although in part the idea behind them might seem intuitive to you. Okay, so the limit laws say the following. So suppose that we have a constant c. And we know that limit as x goes to a of some function equals to L. It exists. In other words, it equals to some value L. And the limit as x goes to a of some other function equals to m. So g approaches m and f approaches m. That means that as x becomes a-like, f becomes L-like. As in the second part, as x becomes a-like, g becomes m-like. Okay, so those are just symbols. All you're saying is that you're getting numbers as you plug in into the function approximations of a. You're getting numbers. Good. So that's a given. So then the question is, what would be the sum of f plus g? So that's pretty easy to imagine that this limit law would hold, and you can prove it rigorously. So think about it, right? This becomes like a number L, and this becomes like the number m. So you expect this to be the limit of the sum. So you expect it to be L plus m. Do you agree? Because this is now almost L and this is almost m. So you expect that the summation is a good approximation to L plus m. Good. And similarly, second law, it's stated separately, but it doesn't have to be. The limit of the difference is the difference of the limits, right? Because this seems to become L and this seems to become m. So we have like L minus m. Good. L minus m. And if I multiply by a constant, if I take a function and I multiply it by a constant, and this function, this number is morphing into L, I'm expecting I will have c times L. Good. So limit of a function times a constant, I can factor the constant out of the limit. That's the idea. Okay. And that also holds for products. You see? So if a function here f becomes L and g becomes m, then the limit of their product will be like L times m. That might seem to you like it's intuitive. I hope it does. But if you think about it a bit deeper, then you get worried. Okay. So if I may pause, do you remember, guys, that question? I'm not sure if it's a good moment to pause, but I just wonder about your intuition. Why I'm trying to tell you, you should be always very concerned if you think something is obvious. It's nice if you think that those laws are obvious, but it's also at some point something that you should be concerned about. Well, have you considered that problem, this game, right? So suppose you have to pay membership fees by tossing a die, and you toss this die until you get the pattern 5-6 for the first time. You can imagine that, correct, guys? And you pay the number of tosses. So the minimum number of tosses required obviously is $2. So you have to pay at least $2 membership fee, at least, right? Because the best way it can happen is first you get a 5, then you get a 6. But you toss it basically until you get the pattern 5 followed by 6. That's one game. And the second game is you do the same thing, but now you have to get the pattern 5 and 5. So just a quick sideway question. I just want to gauge your intuition, if it exists there, and type in the comments, please. I would really appreciate it. What do you think is the cheaper game? Which game would you prefer to play? Or maybe they are the same games. In other words, there's no difference. Play this game or that game, you end up paying the same price. So Gabriel, thank you for saying same. And I want to see what the others would say, please. Same. Go on. You understood, everybody understood my question, right? It seems very intuitive, very simple, correct? Correct? Right, because let's say the probability of rolling a 5-5 is 1 out of 36. Many people even never have taken probability. You have a sense for it, and the probability of rolling, 5-5 or 5-6 is the same because it's for one time, right? Because it's 1 out of 36 chance. So everybody agrees it's the same for this game. Intuitive, right? Very intuitive, correct? And any other question? Anybody wants to contribute? I don't see 30 people, so maybe some are sleeping. So you prove your existence when you write to me something, right? I always need a proof of existence. That's what we do in mathematics. Okay, so let me tell you, you see, none of you are correct. The answer is on average, and I was very proud of it. I was very excited. You know, you get a high sometimes when you figure something out. I had this very smart student, and he's a computer scientist, right? And he bothered me with this question for help. I've sent you a bunch of them, right? People sometimes torture me. So I calculated that on average, you will pay for the first game when it's 5-6, you will pay $36 on average. For the second game, on average, you pay $42. It's not the same. You see? And you see, and I told you, that's why I try to invite you to the probability class. I try to show you, right? So guys, I am glad if something seems intuitive, but you should always be very concerned, right? Your intuition is often very wrong. It's often undeveloped. If you think something is simple, you're wrong usually, right? In probability, you're almost wrong, right? This German guy also argued with me. You see, there's so many things that are very complicated. And of course, the computer guy did a simulation, right? We can show you afterwards, right? It's pretty cool. He simulated 100,000 games, and the average came out to be 35.9 something, right? And in the first game, and in the second 42.0 for the simulation, right? Which proves my point, right? So on average, you would get you would get what I said for the prices. My brother, after I told him, he actually gave a pretty intuitive explanation of that. Maybe afterwards I'll tell you. Okay, but let's return back to the topics. And right, guys, I hope you understand my point here, right? So people have very narrow tunnel vision, right? They ask, why do I need this, right? So they ask, why do I need a limit? And then you see, if you thought about it a little, you might ask me, why do I need just this? Why do I need a narrow? Or why do I need this, right? So what you really want to develop, it's something very holistic, very difficult. You want to develop a feel for things, right? Or a process, an ability to deal with new situations and figure things out. That's the best thing that you can possibly develop. Very difficult, okay? Anyhow, back to this topic. And the one thing I would like to ask again, right? We can do a lecture where we prove why those things are, we prove what limits are rigorously. It's not difficult, but it takes some time to understand it. And I would like afterwards for you to vote whether or not you want that lecture or you want me to keep things, simple, right? So what we can imagine is, again, F becomes like the number L and G becomes like the number M. So the summation will be like L plus M. And for all the other calculations, we should imagine things are simple, correct? They end up in this case being fairly simple. Also with a quotient, if I have F divided by G, you think of the numerator as morphing to L and the denominator morphing to M. So the ratio will be L over M, unless of course the denominator is 0. Okay, then it doesn't apply. If the denominator is 0, and then this calculation L over M is meaningless because I cannot divide by 0.
Thank you.
Say it again. Somebody was saying something. Could you say it again, please? Dragon, you want to say something?
Andy Reid, Kyle Kuzma, and Anthony Davis. Off the bench, I have Rajon Rondo, Alex Caruso, Markieff Morris, Dwight Howard, and JaVale.
Somebody is what? Watching the news or enjoying something else? There will not be other joys in my class.
Gordon, Robert Covington, and PJ Tucker. And off the bench, I got Austin Rivers, Ben McLemore, Daniel House Jr.
Sorry, Dragon. Maybe it's somebody else. I don't know. Who is talking?
They're coming off a relatively easy 5.
Okay. Arif, please be part of the class. Okay. Here is the next question, guys. Okay, so it's also using graphs. Can you see this? What I want you to do is, you see this graph? There is the blue curve is F and the red curve is G. I would like you to try to calculate first A. What's limit as x goes to -2 of F plus 5G? Christian and everybody who answers, thank you so much. Continue, guys. Everybody says what's the answer? All right, so it's pretty easy to do that, right? So what is f? I just figured out what's f at near -2. That seems to be 1 here, right? Seems to be 1. And what is g? G seems to approach, you see there is a hole here, it doesn't matter. We approach either here or along this line. We are approaching this position. We're not there, we're just approaching it, so it's 2. So it's 5 times 2 plus 1 makes it 11. So everybody who said 11 is correct. Now, a slightly more difficult question. What about limit as x goes to 1 of f multiplied by g? Now we are at 1. F multiplied by g. What's the answer here? -2. All right, so notice that f is broken apart, correct? We have a breakage here. So I actually need to consider separately the left-hand limit and the right-hand limit. So if I move from the left, in other words, I'm walking in here. I walk first on the blue line. On the blue line, I walk towards -2 from the left. You agree? If I approach 1, I'm walking as x approaches 1. I will end up going in this direction. I slide all the way to -2. And what about g? G seems to be around 1. So the answer is -2, but only from the left. If I walk on the right, guys, what happens if I walk on the right? So on the f part, this part will merge from the, as I go to 1 plus, will merge towards -1, correct? And g will be 1. So from the right, the limit is -1. From the left, it's -2. And that's the calculation, yes? You see that therefore the limit does not exist because the left hand and the right hand limits do not match. Good? Now, maybe even harder problem. What about the quotient of f over g? So x goes to 2, f over g, what is the quotient? So this is 2. F divided by g, what will be the situation there? That's good. But if you be more precise, you see, sometimes you can say more than doesn't exist. Right? You can specify how it fails to exist exactly.
Wait, can you scroll down a little bit?
Yes, of course. I'm trying to keep the graph in vision, but it's really f over g.
Okay.
Right?
No, I just wanted to see.
You see it?
Thank you.
It?
Yeah.
So that I keep the graph in vision.
Mm-hmm. So.
Right. So good. Are you ready, guys? So there is no problem with f. F approaches the number 1. 1 plus or 1 minus, we can ignore that. It's roughly 1. Yes? F will be 1, but what will g be? If I walk from the right, if I go to 2 plus, g is what? It's -0. It's 0 minus, I'm sorry, right? It's 0 minus. So 1 divided by 0 minus, it's minus infinity. So that means that if I move from the right, the limit as x goes to 2 plus, I get minus infinity. On the other hand, if I move from the left, this is 0 plus. You see, I descend. So y is a positive 0, right? So it's 0 plus, which means it's 1 over 0 plus, and that's positive infinity. Good? So this is the calculation again, guys. Here, as x goes to 2 minus, g is 0 plus. As x goes to 2 plus, g is 0 minus, and f is 1. So what we have From the left, we have 1 over 0 plus, that's plus infinity. And from the right, we have 1 over 0 minus, and that's minus infinity. And again, I say minus infinity out of convenience. What I really mean is that we are falling without bound. And in the previous case with plus infinity, we are rising without bound. And of course, the limit does not exist. It's correct. The limit f over g does not exist, not only because the left and right limits don't match, but because we're not getting numbers. Good? So here is how the limit laws are supposed to quickly, 1 second, Anis. Yes, plus infinity from left, minus infinity from the right. That's what you're saying, Anis, thank you. So here is how limit laws are supposed to build up our ability to very quickly calculate limits for certain functions. So first of all, some basic limits. Limit as x goes to a of the constant function c is what? It's c. Do you understand what that means? What it means is that probably if you don't understand what I'm saying, because I don't like to fail, you might get a c. Yeah, but what it means again, guys, this is a constant. Yeah, I have no idea if you're laughing or whatnot, but yeah, so what it means, it's a constant, right? So think about limit as x goes somewhere of the number 7. 7 doesn't care what x is doing, right? 7 is unaffected, like you are unaffected by my charms, and you're not showing me your faces, right? So the constant functions are constantly not affected. Good? Respond to me, tell me, yes, I understand or whatnot. That makes sense. Good. So this is just symbolic, guys. You see, some people have troubles with it initially, but I actually have trouble with concrete situations. Symbolically, it's much simpler because you see, I right away talk about, the idea is I can talk about all constants. So what I see here, x goes to, let's say, 6 of the number 10. 10 doesn't care what x is doing, right? So the answer is clearly going to be c. As x goes to c, what is c doing? It stays c. Okay. And the other limit, also very trivial. As x goes to some number, what is x going? Well, x is going to that number. So you see, x becomes a-like. What is x doing? It becomes a-like. So that's tautologically true. Make sense? Right. So this part already tells you what this is doing, right? So this means we're getting numbers close to a. What numbers are we getting close to a? So that quickly tells us if we believe in the limit laws, which we can of course prove. We don't have to believe in anything, right? What is this limit? Limit as x goes to a of x squared. This is like a product of two functions that I know. I know what's the limit of x and I know what's the limit of g. So I can apply the product laws of the limit. So I know this is a and this is a. Do you see that? Limit of the product is the product of the limit. Since I know tautologically this part is going to approach a and this part is going to approach a, and I have the product limit, I have a squared. So I right away know that taking limit as x goes to a of x squared gives me the same solution. Well, at least it's a surprising young voice. I was hoping for excitement of sorts, like a pigeon flew into my room or something, right? Some life. So what we have here is a times a is a squared. So notice if I plug in the value into x squared, I get the same thing as if I carry out the limit operation. Not conceptually the same thing, but just the same result ends up being equal. Understand? You with me, guys? Cool. Thank you. And then I can extend it, and I do it for all numbers. My point is that I don't have to waste time constructing any tables or doing anything fancy for functions like x squared, right? I write away any value. If x goes to 7 of x squared, I get 7 squared. If x goes to pi, I get pi squared, right? I just plug in. But notice, guys, so some students make this mistake. They say, oh, just plug in the value. That's coincidental, right? The process of taking the limit coincidentally equals, gives you the same result as if you plugged in, okay? What you do when you're asked to calculate limit, you're asked to put in inputs instead of the x that are very close to a, that are a-like, but never actual a. It's just for this limit, the result is the same as if you just plugged in a, right? The tendency is the same as to just plug in a. So now if you take limit as x goes to a of x cubed, Now it's the same as x squared times x. I now know from the previous example what's x squared. It's now a squared. And now x, I know again, it's a trivial limit. So it's a squared times a, and I get a cubed. You understand? So I recursively use the limit laws, in this case, the product law, to figure out what's the solution to limit of x squares, of x cubes, and in general of x to the power of n, where n is an integer. It's just going to be a to the power of n. I just plug in. Good. I just use the repeated application of limit laws. So if I know that the limit laws are true, I am certain that this calculation is correct without needing any justification, any tables, anything. Good. And let's say evaluate the following, and I will not see each step. I will show you, but try to figure out what those limits are, and try just for now justify how do you do that, right? So using limit laws, of course. That's fine, Dragon. Thank you. One thing is, of course, you don't have to write in the comments how you justify it, but I hope you see step by step why that is true. I will do it. I'll show you below. Thank you, Arif. That ends up roughly being sols, ping. So let's walk through it, okay? So you see this limit, you see what you end up doing is plugging in 5, and we'll reach that conclusion soon enough, and we will not have to think about those limits much. Now, why do you plug in 5? Here is justification step by step using limit laws, okay? So first of all, we apply watch limits. We can break the differences in the sums using laws 2 and 1, right? So we break this. We have limit of the difference is the difference of limits, and the sum is the sum, right? So I have this minus this minus this. That's by limit laws 2 and 1. Then I can factor out the 2. You see, because the limit of a constant times x squared, I can factor out 2. So it's limit as x goes to 5 of x squared. Here I can factor out the 3. So it's minus 3, limit as x goes to 5, and finally x goes to 5 or 4, okay? You see what I'm saying, right? So this we already calculated. We know limit of x squared for any values end up being the same as plugging in the values. So we plug in 5 squared, here we plug in 5, and here 4 is not affected by the limit. So we get the same expression as if we just plugged in 5. So you understand, guys, again, I want to emphasize it again. Limit is not the same as plug in the value 5. So limit as x goes to 5 does not mean I plug 5. It just ends up being that the result is the same as when I plug in 5. So I don't have to worry about it, right? So to calculate it, I can just plug in 5. And this is the step-by-step justification. For the second problem, I use the quotient law first. So that's law 5. And then I plug in. Because now it's a polynomial, we're going to talk about it. Again, we break it using the other laws 1, 2, and 3. On both numerator and denominator, we calculate it, and it ends up, you just plug in minus 2. Good? So why do we get such simple solution? Why is the limit giving us the same thing as just plugging in? So if you think about which types of functions you know, they are not that many, okay? There are not many functions. So here is a question for you. What functions are the simplest functions that you know? What operations were the first operations you learned in a math class in elementary school? What is PEMDAS, Zainbar? What is PEMDAS, please? Zainab, I'm sorry. Multiply and subtract. Right, so who knows how it was explained in school? I don't remember, but think about, right, when you actually can calculate something, usually where does it start from? It starts from addition, subtraction, and multiplication, and then possibly division. Yes, those are the basics, but usually first you learn addition, subtraction, and multiplication, correct? Now, some of those operations can be simplified. In other words, you see, when you say subtraction, you can view subtraction as addition of negative numbers, okay? So 5 minus 2 can be thought of as 5 plus minus 2. So if I do that, I can say that subtraction is not a new operation, right? It's just addition by negative numbers, okay? Adding a negative number. So you have the existence of minus 2, minus 3, and I can just add them. And so in other words, then I have the first two operations will be multiplication and addition. Addition and multiplication, to be precise, okay? And therefore, the simplest functions, and they end up being the simplest functions for computers. Computers can carry addition, essentially. And if you can carry addition, you can carry multiplication. So at least multiplication by rational numbers, okay? So the simplest functions is therefore ones that only use a sequence of operations which are addition and multiplication a bunch of times, okay? So you only use those basic algebraic operations. So here is an example, right? So the function takes an input, writes 5 plus twice the input minus 7 times input plus 1 plus 2 times input minus 3 squared, you see? So this is involving only addition and multiplication. Of course, when I say subtract 3, I mean add minus 3, okay? So that's why I can say addition and multiplication. And this, look at it, this function I can rearrange in terms of powers of x. If I rearrange it, you see I expand it, simplify, I can write it as all the terms, I add them up, that don't involve x, it's x to the 0. Next, all the terms that involve multiplication by x once. Next, all the terms that involve by multiplication x twice. You follow what I'm saying, guys? I group it around. So x is, what is x? X is just the input, right? So how many times did I use multiplication of the input? Here, I did not use, so I gather terms. Here, I did not use the input at all. So I can gather it and make a number out of it. Next, I see basically I can gather it in such a way that I used multiplication by the input once. Next, where I see the multiplication by the input twice. That's what the x squared means, okay? I multiplied x twice, and maybe in other bigger expressions, I might have other terms. So those are called polynomials, okay? So 16 minus 17x plus 2x squared is just, I can rephrase it this way by grouping how many, by number of multiplications of the input, okay? So that's a polynomial. Yeah, I put like terms together. I just make the presentation organized, right? I decided to organize the function based on the number of times I multiply the input. Okay, so in some parts I multiply the input no times. Here I multiply the input once, and here I multiply the input twice. That's an organizational presentation. I could organize it other ways. Okay, so here by increasing order, just 0 multiplication by x, 1 multiplication by x, 2 multiplication by x. So that's what a polynomial is. A polynomial is a function that its operation can be stated as follows, right? It's just a constant a0 plus a constant a1 times x plus a constant a2 times x squared, all the way a constant times x to the n. And the idea, guys, when you think about what this is saying, this is only saying that I only used addition and multiplication, and I grouped it based on the number of times I multiplied by x, by the input. Make sense? So let's see how good you are, right? So you are studying biology, at least some of you. You might want to know if you're good at categorizing different animals. So polynomials to me are like a species of an animal. Let's see if you can identify that species, if you can recognize it, right? So you see spiders and you say, oh, that's a spider, and that's a spider, and that's a spider, right? So they are all part of the arachnid family, right? So let's see if you're good at doing that for functions. So before we do that, right, so let's just mention, right, polynomials naturally, because I use multiplication here, I don't use division. So n, this is just positive, right? I don't divide by x, I only multiply by x, right? So n is either 0 or positive, and these symbols, it means they are all elements of the real numbers, okay? So I'll just briefly remind you what those symbols mean. So that means part of or belongs to a set. And then let's review notation for numbers. N is the natural numbers. So this is the symbol. You use n with a thick bar, or I do it like it looks like in for you possibly, right? But I write it like this. Okay, so that's natural numbers, and also the numbers 1, 2, 3, 4, and onwards, right? Z is the integers, so they include all whole numbers: 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. And the reason you use the letter Z, it's from German. In German, number is Zahl. Okay, Zahl is the German word for number, so maybe Germans are the ones that coined this term. Q is the set of rational numbers. It's the ratio of integer over another integer, where denominator is not 0. Okay, so Q is just fractions, all fractions. 1 over 7, 5 over 12. And R, the set of real numbers. It's a bit difficult to describe what those are. It's actually a very interesting discussion, but too much of a sideways. If you study this course rigorously, you will begin with discussion of what real numbers are, because there are different calculi, so to speak, right? There is a calculus for real numbers. There is a calculus for complex numbers. It's basically, many of the theorems are consequences. You will see some of them. They are consequences of what you know about the structure of the numbers you're dealing with. What is it that you consider numbers? So for us, I mean, we will take it holistically for now. It just means pretty much, I'm sure, any number you ever encountered, it's a real number, right? I don't think, maybe in school you dealt with something weird. We can actually talk about it. Maybe in school you were made to do something with the number I. By the way, how many of you dealt with the number I, since we're on this topic? In school, did you have to do something with it?
Imaginary numbers?
Imaginary numbers, yes.
Oh, yeah.
Yeah? Oh, I mean, you see, isn't it weird, guys? I mean, I'm sure in school you have no idea. You just whatever, I don't care, right? I'm not going to curse that, you know, what you think, right? It's just okay. So you're saying a positive number times a positive is positive, negative times negative is also positive, but suddenly there is a number that when you multiply by itself, you get -1. But could it be, what could that number be? Could it be negative? Could it be positive? No, right? So what is that? So that seems like, oh, weird, I don't care, right? And let me leave it alone. If at some point you're interested, I'll tell you what those are. So aside from that, I'm pretty sure you have not encountered anything that is not considered a real number, right? Although you do not know what real numbers are. So pi, right, root of 7, all of them are real numbers, but do you know what they are? Now this symbol, sideways horseshoe, that means belongs to. So we have that all the natural numbers are a subset of the integers. The integers are a subset of rational numbers, and rational numbers are a subset of reals. Good. So here is your next task, guys. You see, so you look at expressions A through F, and your goal is to classify, right? Let's see if you're good at deciding this function. What is its species? Is it a spider, so to speak? Is it a polynomial or is it not a polynomial? So for A, let's begin with A. F of x equals to 5, the constant function. You see what it means? It means you put anything in and the output is always 5. What is this function? Is it a polynomial or is it not a polynomial?
Not a polynomial.
Okay, Alexa, thank you for your comment. So a lot of you say no, not a polynomial. Now, guys, you see, when you answer this question, don't forget what the question is asking. So could anybody tell me what does it mean to be a polynomial in very simple terms? So you say something is not, right? When you say something is not or something is, presumably you know what that something is. What is that category, right? So what does it mean that something is a polynomial?
From what I've learned in school, a polynomial is like an equation with like multiple like numbers and variables. Like
too big. There are many equations with. First of all, equation and functions are not the same thing. Equation is when you have one thing equal to something else, and you have to possibly figure what makes
an expression, I think.
The expression or the formula, right? So equation is just not the right word. I sometimes myself use that incorrectly, but you should know equation is not the right form, right? You say equation because you see something equals to something, but here you express something else. You mean it's defined to be, right? So this tells you plug something in, and that's what you get out for your input, okay? Okay? So I think, guys, again, here is, think of it holistically, right? So a polynomial is any function that you can only describe, that you can describe with only using addition and multiplication. You understand? That's what it is. Forget about all complicated definitions. It's a function whose inner workings, whose mechanism you can describe using only addition and multiplication. Does it make sense? That's what I try to illustrate again with this example. Why is this a polynomial? Look at it. Do you see the operations I carried? The operations I carried were, here they are, right? Where is it? Were only addition and multiplication. Good? And then I realized that if I carry addition and multiplication, guys, x should not be mysterious. There is no such thing as an x. What this means is that's the input, right? So how does a function work? It's a machine. You put something in and then operation begins and something comes out. You understand? It's like a digestive process. It's like when you go to a vending machine, right? You press the number 1, 2 and Coca-Cola comes out. That's a machine. You understand? Because you gave the input x is 1, 2, and the output is Coca-Cola. It's a machine that transforms numbers into Coca-Cola cans or something like that. Okay, so a polynomial is a machine that transforms numbers into numbers. We're dealing right now with functions mostly that transform one set of numbers to another set of numbers. And then the question is, how is the transformation happening? You are describing the mechanism, right? You're describing the factory. So this is like what you put in the belly. I think of digestive system actually. You see, so that's you put into the digestive system of the function some number, and what is it going to do to the number? It will write 5 plus twice the number minus 7 times the number plus 1 plus 2 number minus 3 squared. You understand? So x is just a symbol to say number. It just tries to give you an idea of how the operation is happening, but there is no such thing as an x, really. Understand? Try to remember that. But I can organize this presentation differently. I can organize it based on what? I can organize it based on how many times is the input utilized. You agree? So the input utilized will be utilize it multiply it once by itself, or multiply it 0 times by itself, or twice by itself, etc. You understand? This is now that's why polynomials look they are presented this way, because they're just organizationally pleasing to the eye. This organizes the operations. They don't have to be organized this way. Notice here I did not organize them this way, right? I just organized them by how many times the input is used, and when you think about it, you realize that it's always brought into this form. If it's only using addition and multiplication and the input is there, it would always be of that form. Okay, you see how I order it. Good. So that's the general ordering. You realize that if it uses addition and multiplication, I can always bring it into this form. Good. I hope you understand, guys, why. You can try coming up with, try it. It's a very good game. Play around. Write any sort of operations where you have addition and multiplication only. Subtraction, I explained to you, it's addition, but with negative numbers, right? So only addition and multiplication, and what is happening to the input. And then see if you can reorganize it and recognize that it's always possible to put it in this form, okay? And now back to the question, is this a polynomial? Does it, in other words, the question is what? Could anybody, before answering it, tell me what am I asking? Is this function a polynomial? I'm asking what?
Is this a machine that turns numbers into numbers? No.
No, it does, because it turns any number into 5.
It does?
Of course, it's a machine that turns
okay.
numbers into numbers.
So
but
is it
no,
considered
careful. That's not enough for being polynomial. First of all, it turns numbers into numbers. Okay. In this case, when it says it's equal to 5, it means it will turn every number into a 5. Everything you put in, it will turn into a 5. That's what this means. Okay. It will digest anything and make it into a 5. It would be 7, it will make it a 5. It will be 12, it will make it a 5. Good. Now, okay, so obviously it turns numbers into numbers. That's part of being a polynomial. But is it enough? Is it a polynomial? What am I asking? So is it a machine that turns numbers into numbers, but more needs to be said? So guys, first, before you answer it, I just, I want you to tell me, what is my question asking to begin with, right? If I say it's a polynomial, did you follow my explanation? If so, please guys tell me, before answering whether or not it's a polynomial, what am I truly asking? It has to be at ground level, right? If it's like complicated words, usually mean obfuscation, no understanding. What am I asking? If you study computer science, if you study any application, it's very important what I'm asking.
Okay, so in addition to asking if this is a machine that turns other numbers into other numbers.
Turns numbers to numbers, yes.
Yeah, it turns numbers to numbers. That's just half of it, right?
That's just all functions we're dealing in this course. That's all they do, right? We are not dealing with soda machines, right? They turn numbers into soda cans, right? Or so there are many functions. A function is anything where you put something in, and for that you get one thing out. Okay, it's like a digestion system. You digest it, process it, and it's a factor, and it pushes something out. Right? So raw materials go in, and product comes out. That's all functions. Now the functions we deal in calculus, they are the type that transform a set of numbers into another set of numbers. Okay. Oh, Joshua, good. Glad that you're back. So, back to my question, guys. Polynomials. I want an explanation from you. What is a polynomial? Very simple explanation, not anything complicated with, big words. Give me a simple explanation. Come on, guys. Such deep silence. All right. Let's try even. Yes, I think you missed entirely what I said. Let's see if you can do that for. Describe to me a zebra. How would I recognize if I see a zebra, please? You go to the zoo. You see, everything I see is very vague. A variable that can be used in several terms. Black and white stripes. Wonderful, guys. You see, it's simple. You're not black and white stripes. That's not enough, right? Of course. But you already tell me something that would help me recognize a zebra. Correct? So, right. So you see, you understand it. And then let's say, how would I tell? So let's say if an animal has 4 legs, is it an ant? So not 4 legs, my apologies, 4 legs on each side, 8 legs altogether, right? Is it an ant? Again, guys, no, probably not. Ants don't have 8 legs, they have 6. Yes? It's just a matter of recognition. So here is again, what is a polynomial, guys? A polynomial is a function that can do whatever it does using only operations of multiplication and addition. Do you understand? If only multiplication and addition are required to do the digestion, then it's a polynomial. Does it make sense? Every function we study, think about it, guys. Every function we study will process a number and make it into something else, possibly, right? It processes numbers to numbers. So the question is, how is the digestion happening? So if the operations that are needed to do the manufacturing only involve multiplication and addition, then it is a polynomial. And you can realize that every operation where every time you only need to use multiplication and addition, that's how it would look. You follow? I can organize it by in according to how many times x is used. Yes, well, subtraction, but again, is part of addition, because if I take 5 minus 2, it's the same as 5 plus minus 2. Are you following? So when I say multiplication and addition, I of course mean subtraction, because subtraction is part of addition. Good, and that's what you get if you can organize it this way. Are you with me? So if you understood this explanation, please type yes. And it's a big deal, guys, because you see, I can show you. Maybe I hope I will live to the time when you understand it. It's extremely significant whether something is a polynomial or not. It's extremely significant in your ability to simulate it on the computer, for example. So again, A, is it a polynomial? And here's how you figure out the answer. Is there any operation beyond addition and multiplication that's required to process the digestion here? You see, if there is necessarily another operation that cannot be simulated by multiplication and addition, then it is not a polynomial. Okay. If there is no operation necessary beyond, you see, it's polynomials is basically this. It's the words that you can express using only addition and multiplication. What can you express using only addition and multiplication? What can you simulate with it, right? Okay, so if you only know addition and multiplication, would you be able to simulate this function?
Okay, Professor, for in order to reiterate real quick, so basically a polynomial is a machine that turns numbers into numbers. In addition, it also is a descriptor for the process of it.
Well, that's you know, that's almost good. That's almost perfect. It's just you have to mention this: polynomial turns numbers to numbers. That's every function we will see in calculus, right? Turns numbers to numbers. Second part is it can do so only using addition and multiplication. So you can describe what the function is doing using only addition and multiplication. Maybe you might imagine everything can be described using addition and multiplication, or maybe you can imagine that some things cannot be done, right? So it's this, guys, right? How many things can you say if you just have certain words, right? So if you only know I and am, how many things can you say, right? I am I, right? So this is a similar thing. It's a bit like with the language. The operations that is understandable is just addition and multiplication here, right? If those are the only operations used, then it's a polynomial.
Okay.
And then by thinking about it, you realize that you always can describe this operation of addition and multiplication by grouping together how many times was x multiplied by itself. It can always be written like this. Understand? But really the essence is addition and multiplication. That's the essence. Subtraction, of course, is addition of negative numbers. Good? So back to this question again, guys. You might think it's not important, but it's not a small thing at all. Because later I will ask you what is a polynomial. I'll ask you if trigonometric functions are polynomials. And this has extreme significance to everything you do in mathematics, if you ever do anything there, okay? Because, or simulation, okay? So is this is it a polynomial?
No.
Why no, Alexa?
Because it's not using addition or subtraction. I mean, sorry, addition or multiplication.
I see. Well, your point is very, very good. Except, you see, here is how you think. It's incorrect only because of that, right? You don't need to use anything if you don't want to. But if you use something, it can only be addition and multiplication. You understand? Nothing beyond addition and multiplication has to be used. So the answer is, it is a polynomial. It is a polynomial where, because again, it is within your vocabulary. You actually don't even need any operation. You just right away split 5 no matter what, okay? So it is a polynomial, and you can see it's a polynomial because you can set, let's say, the coefficients. You can say 5 plus 0 times x plus 0 times x squared, etc. You see, so you did not bother using x at all here. So it is a polynomial. All constant functions, 0 is also a polynomial, right? All of them are polynomials because you don't ever use anything beyond addition and multiplication. Perfect? Now let's go to b, guys. Is b a polynomial? And of course, why or why not? Well, every function will tell you what it does to the input. So you need to say, what will the function do to an input, okay? And if what the function does to the input can be described only using addition and multiplication, then it's a polynomial. You understand? So is b a polynomial or not a polynomial, guys? b is a polynomial. Well, go on. Yes. Good, good. Everybody is in agreement that b is a polynomial. You see, what do? I take the input, I multiply the input by itself 7 times and then by -3. So for the first part, I only use multiplication, correct? Then here I used addition, here I multiply the input twice by itself and then by 5. So again, I only used a multiplication and addition, and here I add a number. So again, I used only addition there, right? So it's clearly a polynomial. You see that? And practice, guys, it's maybe after class, if you want to, we can just have a few examples. So you see, I want you to realize that it can always be arranged like this, where I use by the input, how many times it was multiplied by itself. Here is the next question. Yes, exactly, guys. If you don't need any operations, of course, it's enough. It's within your scope to describe the operation using addition and multiplication. Understand? Because you actually did not bother describing any operations like this. So it's obviously a polynomial. What about C? Let's see about C, guys. That becomes more and more interesting, I hope.
Professor, quick question.
Yes. What's your question?
If I imagine the A, it's like f of x, it's equal to 0 times x plus 5.
0 times x plus 5, precisely. That's what I did in my solution here, you see. 5 plus 0 times x plus 0 times x squared. So I can imagine I use addition and multiplication if I need to, right? I can describe it using addition and multiplication if I have to. If I have to use them, I can do it, right? So if you can describe it using addition, you can do it two things. You can think of it two ways. That's very good that you mentioned. Either you can say, well, if I get 5, I don't need to use any operation, so sure, I can do it. But if you really want to say, well, no, I want you to use addition and multiplication, and I can do something like this. 5 plus 0 times x, etc., right? So I can describe this using only addition and multiplication. That's the point. So I want to know for C, guys, is C a polynomial? Do I only use addition and multiplication? Okay, so think about it carefully, right? So is this possible to is this only using addition and multiplication? And if not, is it possible to find another expression that would only use addition and multiplication? Okay, so some people notice there is division. Wonderful. The negative exponent means there is division. So let's look at it, guys. Here, right? If I have x to the -2, that's the same as 1 over x squared. I think later we can talk about it at length if you don't know why this is not arbitrary, okay? So here I use division. I use an extra operation, but is that enough to conclude that it's not a polynomial? So I use division here. So the way it's expressed, it's not using it's not using only multiplication and addition. You see, because I have division. Good. Everybody is with me? Cool. Does this mean it's not a polynomial? And if no, then tell me why not. And if yes, tell me why yes. You see, I'm trying to make sure you can classify it correctly.
I think the reason why it's still considered a polynomial is because there is still division, I'm not sorry, multiplication and addition. But like, didn't you say previously that like technically division could also be considered multiplication?
Well, I like what you're saying. You see, so we are not going to consider division a multiplication for one particular reason, right? And I'll show you this, right? So that we will take that into account with rational numbers. You see? So you see, here is the question. So right now, clearly I'm using division. Let's say if I use division, then I use more than in the scope of my vocabulary. Right, so what is written here is not in polynomial form because I use addition, multiplication, and I also use division. Yes. Now my question is, well, is this enough to know that it's not a polynomial, or you see clearly by this form already we're using one extra operation that we are not allowing. It's a polynomial only allow addition and multiplication, and addition means subtraction as well. Okay. Because you see, the reason I don't want to consider division the same way is because I have division by 0, for example, right? And there is a dangerous situation. Multiplication works all the time. Division does not work when I divide by 0. Okay, that's why I will keep it as a separate category.
Okay.
Good. So this is not polynomial form because there are 3 types of operation: addition, multiplication, and division. But does it mean the function is not a polynomial? And what is my question asking, guys? Can you figure out? Okay, so one person, Ibad, says I cannot rewrite it, so the division is not involved. But how do you know that? That's excellent point. Excellent point. Right. The question is, can I rewrite so that I'm not using division? You understand? Maybe division is used there, but maybe I can rewrite in a way that division will not be used, and only multiplication and addition. It's like describe without using division. Can I do that? And how do you know yes or no? You follow my question, guys? Or are you completely confused? Zainab, you understand? Great. And the rest of you, do you understand? Type yes if you understand. It's a very, guys. So it's not. You might think I'm pencil pushing or whatever it's called, but no, it's a very big deal. Right? It's how you understand things truly. Right? Polynomials play huge role. Yeah. So people say you don't believe you can write it. You understand? So the question is this: you see, do I have to use division to describe this operation, or can I find a clever way around it where I don't use division? Okay, and here the answer is, let me tell you how I know that the answer is no. If this is a function, right? So if it's a polynomial, I can describe the operation by using only addition and multiplication. If I only use addition and multiplication, I can put in any number. If I put any number inside, then it should work. You agree? Because addition and multiplication works with every number. Are you with me? Right? Trinomial, those are just specific words. Trinomial means you have three terms. More importantly, is h a polynomial? It's definitely not in polynomial form, but maybe if I'm clever enough, I can write this formula without using division, figure out a way around it, right? So reprogram it and don't use division. But the answer is I cannot, as some of you suspected. And how do I know I cannot? If I could, plugging in 0 would produce an answer. You see why it would produce an answer? Because well, any number can be processed by addition and multiplication. There will not be an error. But look at it, I plug 0 here, I have 1 over 0 that's undefined. You see, if I plug 0, I have 7 times 0 plus 3 and 1 over 0. So it's undefined at 0, which means I cannot avoid, I cannot express it, at least using, maybe I can express it without using division, but definitely not by using multiplication and addition alone. Do you get my explanation, guys? I found a way, because you see, I reason this way. It's not that I'm not clever enough, right? Because if it's only multiplication and only addition, that is enough to describe the process, then I should be able to do so for any number. That is, if I put any number into the function, it should digest that number. It should process it and produce a number. But I see that if I put 0 here, I have 1 over 0 and digestion is spoiled. It's not going to work. You follow? So I found one thing, that if it, so I found a contradiction, right? So I think like this. Okay, suppose I figured out how to express it only using addition and multiplication. I put it in polynomial form. You put any number into polynomial form, you will always get another number out, because it will be a bunch of multiplications and additions. But here, I put 0 in and I don't get anything out. It's undefined. So therefore, it's not a polynomial. Good? Okay, are you with me? Write yes if you understood, and let's move to the next problem. And guys, if you have the nerve for it, I can show you something very impressive eventually with those things. So if you study computer science, those are important questions. Okay, let's try to play this game slightly longer. What about D? Is D a polynomial? So this is D. Is this a polynomial? Notice there is a division here, right? The question is this a polynomial? And we will see that in a moment. So if it's yes or not, I would like to also hear your justification, right? So Chris, you say it can be simplified to x squared. That's a very interesting, very great point that you're saying. Exactly, Joshua. So Joshua noticed something, okay? So let's do D now, guys. Are you with me? Let's do D, and we will determine what it is. So several of you did something quite interesting. Look at it, right? K of x, I can factor out an x squared, and then we have x plus 1 and x plus 1. They can cross out. But the problem is I cross them out under the assumption that x is not minus 1. So it's x squared unless x is equal to minus 1. So therefore, this function cannot digest values at minus 1, which means it's, strictly speaking, it's not a polynomial. But of course, this is called removable singularity. So in our class, just to be sticklers, we will say this is not a polynomial, because you see, you cross out and simplify it to x squared only under the assumption that x is not minus 1. Do you see that? You cannot cross it out and simplify if x is minus 1. So it's not a polynomial, strictly speaking, but in more advanced courses, Christian, it will be considered a polynomial because it's a trivial, trivial situation, okay? But strictly speaking, it is not. What about the next part, E? Is E a polynomial? So here we have a division, we have x squared plus 1, right? So is this a polynomial, v of x? Yes, so E, and that's Christian's point here, right? We can simplify it. We never have zeros on the denominator, right? No matter what I plug, the number squared plus 1 is never 0. Good? So E, here it is, right? I can factor out x squared out of x squared plus 1, and I can always cross them out, and the answer is x squared, okay? So v of x is the same as x squared. I can do away with division. So even though I have division here, I can actually re-express the function and put here polynomial form. Understand? So just because something does not look like a polynomial does not make it not a polynomial. In this case, I can get rid of the division operation, and I can be sufficient. I can sufficiently do everything with addition and multiplication. Now, final question is f. It's ix 5x to the 1/2 plus 2x cubed. Is this a polynomial? Yes, so, and you can not only because of that, but because I can get away, do away with division. I can express it in polynomial form, okay? So in E, I'm certain that I'm able to do away with division. So I only use addition and multiplication. You need a square root, but the question is maybe if you're clever, you don't. That's the question. You know the square root is not multiplication. Think about it. It's a much more complicated operation, right? It's inverse of multiplication, right? You don't know exactly how to do the calculation for square roots. It's not such a simple operation as when you multiply. Can I deal away with the square root or not? And how do you know? You know, nobody maybe ask you that. Maybe somebody smart can figure out how to write this operation without using square root. The question is, can you show that it's not true? You understand what I'm saying? It's almost like, it's in sense like programming. How do you know that something can or cannot be done? Sometimes those questions are very difficult.
So what was the question again? Sorry. How do you know if you can prove something? We're talking about
Yes,
F,
so
right?
those are always very tough questions, right? So you see, you learn in school in such very trivial ways. Just look at something one moment, and then right away you either dismiss it or ignore it. And the question is here, you see, we use the square root. Okay, square root is a pretty complicated operation. You even figure out, you learn it much later. In fact, because you cannot, you see, you can always calculate number multiplied by another number. You can figure it out. You have multiplication that you can perform on paper, right? But square root, if I ask you what's the square root of 5, most of you will not know what to do, right? You will be stuck. You need a calculator for some reason, right? So what's the operation? The question is, can I replace this function by an operation that does not involve the square root, but does the same thing? You understand? It's like you're trying to use your smaller vocabulary to describe something more, right? So here we see addition, multiplication, and square root is used. Right? Can I reduce, like here in E, I was able to reduce to a situation where I did not use division, you understand? So it's a polynomial if you can reduce to the situation where you don't need to use anything but addition and multiplication. That's really what a polynomial is, okay? That's why it's such an important function. The question is, can you do it for f? And if not, how do you know that you cannot? And if yes, maybe how do you know that you could? In general mathematics, some of the hardest questions is to show that something cannot be done, or sometimes that something could be done even without knowing how to do it. But there are arguments that are called non-existence argument. You prove that something cannot be done, and that they tend to be extremely difficult sometimes. You understand what I mean? Let me help you a little bit, right? One easy characteristic, we will learn other characteristics later on. If I only can use addition and multiplication to describe the process, one easy characteristic is that I would be able to do it for all real numbers. Understand? If there is an operation that, well, if I can simulate it only using addition and multiplication works for all numbers. Do you agree? Right? So that would mean that this function will be giving me answers or outputs for all numbers. But does it? So negatives won't work. Here you go. Beautiful, Christian, right? So if I put in, let's say, -1, at least in our case, if we're using real numbers, -1, root of -1 does not exist in the sense of real numbers. So it's not a polynomial. You see, so that was in this case a simple way to show that it cannot be. Because you see what I'm saying. I imagine, okay, suppose you were clever enough and you figured out a polynomial formula. If you figured out a polynomial formula, this formula should work for any input. Right? Any real number. But here I clearly see that I don't have roots of negative numbers. So it's not a polynomial. Clever, you understand, right? We'll learn many other ways. You follow me, Alexa? Excellent, guys. And everybody else, you follow me, guys, right? So you begin to understand it, right? So functions will hopefully start looking to you like animals that you see in the zoo and be interesting to you in that same sense, right? You might see one animal eat another animal in a curious way, and you would see that with functions. Okay. Okay, good. So we cannot plug negative numbers. Okay. Now here is one theorem. So guys, are you fuming? Are you still with me? You're able to think? Circuits are still working? Tell me yes, or if you want to break for a moment, talk about something else for a moment, tell me before I go on. So you're not.
Well, can we take a break? Just like
Take a break. A small break. Take a break. Go drink. Eat something quickly, and continue talking to me if you want to. Yeah, good. And again, guys, let's see, what are we doing there? Going back to F. Yes, you will if you. So you see, here is going back to F. What was F? F was this, right? So if you put in any negative number, roots don't digest negative numbers, because when you say what's the root of -5, or let's say what's the root of -25, right? -25 means I want to find a number that when multiplied by itself will give me -25. Well, if it's a real number, it's either 0 or positive or negative. 0 clearly doesn't work. Any positive number multiplied by itself is positive, and any negative number multiplied by itself is negative. Sorry, it's positive again, right? So are you there, guys? So negative by themselves, positive by themselves, positive. So there is no way I can get root of -25, so it seems. Yeah, so you cannot take root, so you cannot plug negative numbers into the root, Ibad. And of course, one important question is, well, why can't I do it? Why negative multiplied by a negative is positive? Anybody wants to tell me that? Let's see if you know that. You never thought about it? Why negative times negative is positive? But why would the negative signs cancel out? You see, if you do not see why a negative times negative is positive, then it should not be paradoxical to you that imaginary numbers exist, right? Like, you know, what's so paradoxical about it if you just somebody said negative times negative cannot be positive? Maybe the person is wrong. Why, Dragon? Why negative of something negative is positive? Yeah, it's of course a difficult course, guys, but it's too bad you're not coming to the probability too much, right? It's the closest subject that in terms of even money, right? There are some people that go into actuarial science or yeah, it's a lot of it's real math there. So what? Irvin, you say all negative numbers are positive numbers multiplied by -1. So how would you see, one thing is, how would you know that? How would you tell? Definitely that it has to be true. You can take for now for granted that negative times positive is negative. You might imagine it this way, right? So it's a, if you have a debt of $10 multiplied by 5, it means you increased your debt by 5. So you have now -$50. You're in -$50 in debt, right? So negative times positive, it can actually also be justified. It has to be justified rigorously, but let's say negative times positive seems intuitively true that it would be negative. But why negative times negative? Why would negative ones cancel out? Why do they cancel out? Interesting, right, guys? Oh, hello, Alexa. Nice that you came back. All right, so all right, our lecture is almost over. Before I move on, I need your input, guys. You see, so the next lecture could either be, you know, we go on with continuity or not, or we talk about delta epsilon. I just want to gauge if you want to talk about it or not. Delta epsilon is the rigorous proof of what limits are. So if yes, type yes, and I'll write a lecture for it. If you say, oh, I don't want to go over it, I might keep it simple. And you can ask me, of course, if is there any benefit or etc. What do you want to really understand? Yes means do it. I want to know what delta is. Okay.
Yeah, for the delta epsilon thing.
You want to try it? Okay. So
Yeah.
I'll try to explain. It's actually something very simple, but only once you understand it. It's very difficult before you understand it, right?
Okay.
But it's trying to explain this. The water gun analogy, I'll try to explain it as precisely as I can. Okay. So I'll try to write delta epsilon argument. That's my analogy. I was very proud of it. You understand? When you begin being interested in the subject, usually It's because it steers your imagination. It gives you visions of things that otherwise you did not know. So for example, in abstract algebra, you get this feeling that you imagine what God looks at you like, right? So, and I think, well, God doesn't see the difference when you get a flower for your birthday or when you get shot, right? So, and that you get from abstract, that's what I got at least from abstract. Like somebody shoots you with a bullet, same thing, right? Structurally speaking. So you get such ideas. Okay. So, yeah, so what we are going to do now is, so let me just quickly go over. So more people are going to say yes or no. This video, by the way, I already have videos available on it, right? So that's if you're interested, we can talk about in this class. If not, I can suggest the video. So I would like to know more about you guys. I'm afraid to lose you. You understand? I mean, I imagine it happening every moment, especially that when I don't see you. All right. I think because at least the people that talk to me said yes, I might do it, right? But besides, in general, I want to.
Okay, Professor, can you also wait? Does it have to do with delta epsilon, or does it have to do with like the
Right
lecture,
now, no,
the limit laws, the video that you're talking about suggesting?
It's just I taught this class and I recorded videos when I was in the class, so there is a delta epsilon video in the class, but I can do like a lecture through Zoom about it, right? So
okay.
that's what I'm asking, right? So assignments, guys, we still covered very little material, right? So it just begins. We're right now in chapter 2.2. You can try doing exercises from the odd exercises in the book have solutions, and that's how you gauge if you are understanding the material. You solve exercises and see if your solutions are correct on the first trial. If they are correct on the first trial, you are learning adequately. Okay. So right now, here is what I suggest. You're in 2.2. Go into that chapter, 2.2, 2.3, basically, right? And look at the odd numbered exercises that have solutions in the back of the book and try to solve them. Solve a few of them, right? You don't have to solve all of them. Try maybe some simple ones and maybe some later ones. All odd numbered exercises have solution, right? Assignments for this class, etc. Everything you truly have to do is just the exams, right? It's because I would not, I still have to write some of those lectures. I'm still writing them. I wrote only for the other part of the class. And I don't have lectures available until trigonometry. Okay. So basically what I want to say, just this one last thing, is that if we are dealing with a polynomial, then evaluating the limit means you can just plug in the value. There is no difference. And the reason for that is every polynomial can be written in this form. I hope you can try to play around and convince yourself that every polynomial can be written this way. And then I see that I can use the addition and multiplication limit laws, to calculate the limit. So first is addition. So I have limit of the sum is the sum of the limits. And then here I use recursively multiplication. So for x to the n, remember, x squared is using it twice, then x cubed is using it again, then x to the fourth using it again. I can recursively use the limit laws, and then I get the same thing as plugging in the a. And so I see that limits don't give us any new result. If I take limit of a polynomial at a, I get p of a. Okay. And one thing you see, polynomials, the analogy is that of integers. So we speak about base 10 system. The base 10 system. Do we have WhatsApp group to join? You want to join a WhatsApp group? Well, I have a WhatsApp. I don't know if I trust you, you can send me messages through WhatsApp. But then I need to know you better. So what you have here is, let's say, the number 1806. What is it really? Why do we call it base 10 system? Because this is 6 plus 0 times 10 plus 8 times 10 squared plus 1 times 10 cubed, which is very similar to the polynomial 6 plus 8 x squared plus x cubed. You see that? This is the polynomial, and you plug in 10 into this polynomial and you get this number. So base 10, or basically your integers are polynomials. In essence, there is a very strong connection between integers and polynomials. And they are just like integers are the simplest numbers, polynomials are the simplest functions. So maybe one last question, guys, guess what's the next level of difficulty for functions? We know that we have addition, multiplication. What other operation do we add to make it slightly more difficult?
Division.
Exactly. So if you have addition, multiplication, and division, then that's called rational function, okay? And let me ask you this question. Is any polynomial also a rational function?
No,
Why not?
because it doesn't have. Because a polynomial usually has multiplication and addition.
Yes, but rational functions are not polynomials necessarily, but the other way around. Are all polynomials rational functions?
Mm.
You see? Think about this, right? So it's a simpler question than it sounds, right? So polynomials are everything I can express using addition, multiplication. Rational functions, everything I can express using addition, multiplication, and division. So I have more options, which means what?
Mhm.
Which means yes, of course, right? Because if I have rational functions, I don't have to use any of the operations. I'm just allowed to use more operations. You see? So if you have addition, multiplication, and division, you're allowed to use more operations. Then clearly every polynomial is a rational function. I'm just not using division.
But not every rational function is a polynomial.
Because you need more functioning, right? More operations. So polynomial, you can only use two. Sometimes you have to use division. Sometimes you don't. But if you have more operations, you have greater flexibility. So rational functions is a bigger category. And if I add roots, that's even bigger category, because if I have addition, multiplication, division, and all sorts of roots, those are called algebraic functions. They're even a bigger category. Algebraic function is one of the big categories that we have here. So almost everything you see until you get to trigonometric functions, exponentials are algebraic. Make sense? Because the more operations, the bigger is the category, the more flexibility you have. You can just turn off certain functions, certain operations, and then you have the smaller category. Good. So that's good enough for today. If you have any questions, you're welcome to stay. I will stop the recording, and otherwise have a good day.